Just quick intro to myself. So Steve Griffith, I'm a Principal Technical Specialist, aka GBB, Global Black Belt, covering app innovation. Formerly, we were called Cloud Native, but we're kind of more broad than just Cloud Native. Our team covers functions and app service and really any modern app development in Azure. So my focus is a bit more on the Kubernetes front these days, focusing on helping our customers build large-scale enterprise solutions on Kubernetes, all of our container solutions in general. From a background perspective, I came from Accenture, where I spent 13 years in a group that ultimately became something called Accenture Software, which was building software solutions for customers and selling them. That group eventually became Duck Creek Technologies, which you may come across if you ever work in the insurance space. I was the lead technical architect for Duck Creek for a number of years, again, working on application platform architecture and eventually running their cloud engineering business, at least from a technical perspective. I've been with Microsoft for 6 years. I was in the CSU before coming over to the GBB team. In the CSU, I covered entertainment and media customers, so all the kind of large US-based entertainment media customers you can think of. I worked with most of those. As far as likes, I love digging into the low-level details of things. I love to understand the internal workings of everything that I work with. I spend a lot of time in Linux, a lot of time in networking. I play guitar, I surf, I like long walks on the beach. On the dislike side, I hate not understanding how something works, and it's to my detriment. When someone asks me a question, it can ruin my entire day as far as productivity is concerned, because I'll just spin off and spend the entire day digging deep into how something works. I also don't like parsley. I think it's disgusting. I don't know why we put it on food. It tastes like yard clippings. And that's all I have to say about that. The learning objectives for this session, we're going to dig into the fundamentals of container networking, Kubernetes networking, right? To really understand how things come together within that space. We're going to use the above to explain a bit about AKS networking architecture. You're not going to spend a ton of time specifically on kind of drawing big picture AKS network design. We're not going to spend time talking about outbound type and route tables and things like this. I really want to focus more on the network stack itself and what pieces come into play to make a container run in Kubernetes and make it accessible on a network. We're going to quickly diagnose a network container, a container network issue. We're going to do it in the most painful way possible to really see all of the pieces in the stack. This is not the way that I'd recommend you actually debug something, but it's going to take you through the tools that you need to debug an issue in the future. All right. So getting into it, first thing I want to make sure is clear is Kubernetes networking isn't magic. Not saying that anyone really believes that it's magic, obviously, but I think there's this sense that people avoid networking conversations. I know because I get pulled into them all the time. And for things that are seemingly simple, I think it's largely because people are just generally kind of afraid to dig in on networking. They're afraid that there's some kind of higher level of complexity than most people are ready for, when really it's not. It's all pretty basic in the components that are used. So we're going to run through and establish some of the fundamental components right now, and then we'll get into the debugging. But I threw this meme in there because it's like, when it comes down to it, who is in our network, who is in our cluster doing things that make networking work in Kubernetes? In the end, it comes down to pretty much IP tables and interfaces, right? There's a bunch of agents that are sitting on top of all that, making this magic happen, but really it's IP tables and interfaces for a majority of what you're going to see within Kubernetes. All right. So bear with me, because I'm going to run through some things that many of you, if you're already familiar with Kubernetes, you're already familiar with AKS, this is going to seem maybe a little bit basic, but I think it's important to establish these fundamentals. Most of this I'm just kind of copy and pasting straight from the upstream Kubernetes documentation, so you can go and read that yourself, but I'll give the really quick version here. So first of all, when we talk about key components, one of the most fundamentals is a process called kubelet. So kubelet, and again, I didn't mention this before, sorry. We're going to focus primarily on Linux containers right now. So we're not going to dig into the Windows side, but it's pretty much the same, just using a different set of tools. So kubelet is the process that runs on every single node within your cluster that's responsible for managing the containers on that node, right? So if I say, hey, I'm going to go create this container, the Kubernetes scheduler is going to go and say, okay, well, that should go on this node because it has excess capacity. The kubelet process is watching what Kubernetes is assigning to different nodes and says, hey, that's for me. And then it does its process to actually get that container running locally on that node. You can see kubelet running just by SSHing into one of your Kubernetes nodes, doing a PS. You can grep kubelet like I showed here. And this long set of flags here is all of the stuff that is setting the configuration for kubelet. And I'm calling out a couple important ones here, well, really just one important one, the network plugin, right? So depending on which network plugin you're using, Kubenet or Azure CNI, which we'll talk about a little bit more, you would see that referenced here. You also see different IP address ranges and things like that within this configuration. But kubelet is really what's doing most of that work, okay? Network plugins. So probably the most fundamental conversation we have with customers and people ask me about and ask my peers about is which network plugin to use. And in Azure, there's really only two options as it stands today. And in Kubernetes, they refer to these as kind of two types, right? So the first type is Kubenet. So Kubenet is from the upstream Kubernetes project. It's what we refer to as an overlay network. So an overlay network, as you can imagine, is a network overlaying another. It's a network on top of a network. So we create through Kubernetes this additional network that sits on top of everything else you have. So you have your Azure subnets and all those things running down here. Your nodes are connected to those subnets. And then you have this other layer that was created on top. And this is why you hear say, hey, make sure you don't have address space overlapping and things like that. Because if you have a network on top of a network that shares common addresses, things can get a little bit funky. But that's an overlay network from the upstream Kubernetes project. There's others out there that fall into the category of container network interface plugins. So let's call them CNI, right? So container network interface is, if you're a programmer, this will sound familiar. It's a specification. It's an interface that defines how you can write a network plugin for Kubernetes. And anyone could do this. You could go spend this afternoon writing your own Kubernetes network plugin, and it will run. You can go and get it running in a Kubernetes cluster if you follow the CNI interface. And there's a ton of them out there. They're typically built by cloud hosting providers, infrastructure hosting providers, right? So we have the Azure CNI, which you've heard of. GCP has one, AWS has one. There's others out in the market from third parties like Isovalent, who manages Cilium, has Cilium CNI. Tigera, who manages Calico, has Calico CNI. Ton of these out there, but fundamentally they all implement the same interface. They're all pluggable into Kubernetes, okay? All right, so now we get into the components inside the cluster. So those are the things that make the cluster run. So kubelet, CNI, and Kubenet, in addition to kubelet, which are two different things. Now let's get into the components. So the lowest level of compute that you'll set up, that you'll define in Kubernetes, is known as a pod. Most of you are probably aware, for the most part, a pod equals a container, more or less. The reality is that a single pod can actually have more than one container in it, so which is useful in a number of circumstances. You may have heard of service mesh. You might have a logging framework that you want to run alongside your application, and you don't want to modify your application code, right, to do that. So having multiple containers within a pod is useful. Pods share common network namespace and storage namespace. They don't share a common process namespace. So what's a namespace? So a namespace, we're not referring to what Kubernetes would call a namespace, which is, again, kind of a grouping of components within Kubernetes. It's within the host itself, within Linux itself. It's the ability to create isolation boundaries, right? So all of these things share common networking. All of these things share common storage. So all the containers within that namespace, within that storage namespace, or within that networking namespace can all share common things. I was mentioning to Wolfgang before we started this call that we're debugging an issue with a customer right now where we are having an issue running .NET 5 next to .NET 6, or sorry, we're having an issue running .NET 6. We were able to create a pod that had 5 and 6 right next to each other, sharing common process namespace so that they can interact at a process level. So really cool things you can do with pods, but fundamentally they're the lowest level of compute that you'll configure within Kubernetes. All right, services. So a service you can think of really, for the most part, is a layer 4 load balancer within your cluster. It's not a appliance. It's not a thing sitting there necessarily running like a load balancer, but it behaves very much like a layer 4 load balancer. And when I say layer 4, for those who aren't familiar, we're talking about load balancing at the TCP level, right? So down there, we're not talking about HTTP, which would be an application level load balancer, where maybe you're doing, path-based routing. We'll talk about that in a second. This is really just dealing with IP addresses, right? So we're saying TCP, UDP, traffic getting routed around within your cluster. That's what a service gives you. There are 4 types of services that Kubernetes provides. The first is cluster IP, right, which you can see right here. The cluster IP is actually a non-routable address space within your cluster. It's actually effectively an overlay network, right? We talked about how Kubenet has overlay networking. The service effectively operates the same way. And in fact, when you create an AKS cluster, you have the option to specify what address space is going to be used for those cluster IPs, right? So this is really just used for internal pod to service routing. So if I have a service, I'm running an application and it needs to talk to another application in the same cluster, it might talk across that cluster IP, okay? But we can't access the cluster IP from outside the cluster. Node port. So node port actually, there's a range of ports that Kubernetes designates to the entire cluster. And if you set your service to be a node port, it will give you one of those ports, and it will give you that port across every single node in the cluster. So if I say, hey, I'm going to go to node 3 at this port, it will find my application. It will route it around to the right place. So basically every node now is accessible, or that application is accessible from every node using that node port. It's not used too often, but it is an option for you. The one that we use probably most commonly is load balancer. So load balancer is the service type that interacts with the hosting provider, right? So you say, hey, I want a service of type load balancer. It will go out there and it will provision in our case, an Azure load balancer, maybe an internal or an external load balancer, depending on what parameters you put on there. Sorry, my cat just tried to jump up and failed miserably. It will create that load balancer for you and manage it for you within the cluster. And this is the way you would expose a service from inside your cluster out to your private network or out to the public internet. If you use kind of a default configuration of that load balancer, it will create a public IP. The last one here is rarely used, at least in my experience with our customers. External name, it basically creates a service that's mapped to an external DNS, right? So if you want to expose a service that routes to some other external DNS, you have that option here as well. All right, keep an eye on the time, 10:15, we're good. Endpoints. This is one of the lesser known components. People tend to operate and just deal with services. And kind of the magic of services is that behind the scenes, they create endpoints. So when you create a service in Kubernetes, you include what's called a selector. So a selector in a service says what backend pods that service should expose. Well, what really happens there is when you set that selector and you say, hey, the selector is for my application pods, right? It goes and finds those application pods and it creates an endpoint, an endpoint for you that includes the IP addresses of those pods. So what you can see here is if you go and you have a service running in your cluster and you say, hey, go get endpoints, kubectl get endpoints, you're going to see your application here. In this case, our Flask app Z. Here's the IP addresses and ports. The selector did that. Selector went out and said, hey, what pods do I have running that match the selector? Oh, these 3 match. Okay, so I'm going to create an endpoint with those addresses on there. Now, the kind of cool thing about endpoints is those IP addresses don't have to be in the cluster, right? So if I jump over here really quick and show you here at my home, I actually have my daughter has a lizard tank, and we have a IoT project that we did together to monitor the temperature on the lizard tank. So I have a Raspberry Pi sitting in the other room. Hopefully this comes back. There we go. I have a Raspberry Pi sitting in the other room that's on my 192 network, right? So my cluster network is 10. This is a AKS cluster that's running in Azure, but I have a site-to-site VPN set up. So this cluster can see my Raspberry Pi at this address, right? So I'm actually able to take that Raspberry Pi that's in the other room that's not part of my Kubernetes cluster, expose it as an endpoint, and then I can actually wrap that as a service. So now my Raspberry Pi, oops, let me make this a little bit smaller. Now that Raspberry Pi that's sitting in the end, or in the other room, is exposed in my cluster as a service. Let me do it one more time so you can see a little better. Right, so here you can see it's using external name, it's pointing to that endpoint address, and we're good to go. I can now talk to that Raspberry Pi from my Kubernetes cluster. So again, little known thing, but it's very important in the way that Kubernetes networking works. All right. Ingress. So we talked already about load balancers and how they're layer 4. So how do we do layer 7? How do I do TLS offload? How do I do host-based routing? How do I do path-based routing? All those things that are kind of application level concerns. That's where an ingress controller comes into play. So Kubernetes has a concept of ingress. It does not itself have an ingress controller. So if you set up a Kubernetes cluster, you don't get an ingress controller. You get a set of specifications for CRDs for how you interact. It's actually not CRDs. It's part of Kubernetes upstream ingress. How you interact with those ingress controllers. So then you can go and install whatever ingress controller you want. You can install Nginx, you can install Traffic, you can install Envoy, whatever your preferred is, and they will partake in that, in that ingress. And you go and create a Kubernetes ingress. You specify, hey, this is the ingress controller that I want this to target, and you'll get all that functionality. So this is where you can do lots of really fun things with, dynamic application routing, right? If you're doing blue-green testing, A/B, all those fun things, ingress controllers help you accomplish that. Okay, and they do that by creating routing rules. You can use App Gateway Ingress Controller, for example. When you create routing rules, it will go and talk to Azure, to the Azure App Gateway, and create those routes for you. Okay, so that laid the fundamentals that we're going to use for the next handful of slides. And we can come back and readdress those at the end if there's any questions about any of those components. So feel free to type those in the chat and we'll come back around at the end. But what we're gonna do now is we're gonna do a bit of a debugging deep dive, okay? So I've created an application. You saw there was that Flask app that I've shown in a few slides. We're gonna go through kind of a fairly painful debugging attempt. We're gonna work really from the top down. This is probably not the way that I would do this debugging in real life, which I mentioned before. But bear with me. I'm gonna take you on this journey. Stick with me because I think that you're gonna hopefully learn some things coming through this, and we'll revisit at the end how we would have maybe done this a little bit faster. Okay. So first of all, let's take a look at the application itself. The application is very basic. It's Flask. I think it's 8 lines of code, which I'll show you the code towards the end of this. But it's basically the equivalent of a Hello World Flask app. In fact, if I clear the screen. Let's curl. Oops, that's the broken one. Let's curl 1. You can see, hey, we have a Flask Docker container, right? I think I copied and pasted this directly from some how to containerize a Flask app example, which I think is interesting because this is exactly the type of thing that someone would copy and paste and run into this issue that we're going to hit here. Okay, so here's my deployment. So my deployment, if you're not familiar, deployment is how you package up an application for Kubernetes. It includes a replica set. A replica set is just how many copies of this pod do we want running, right? So here's my deployment. Here's my replicas. I want 3 replicas. Here's the selector information that we talked about before. And then the specification for the containers, right? So we can have more than one. In this case, I'm just doing 1. It's pulling from my Docker Hub. The app is called Working. I have another one that's called Not Working. Hint, hint, what's causing the issue here. And then I say what ports it should expose, okay? In the top here, I'm exposing the service. So Flask app A should expose ports 5,000. TCP, the target backend port, is 5,000. Obviously could have mismatched those. I could have said 80 to 5,000 if I wanted. And this is what I talked about with that selector, right? So this selector is going to look for containers that match that, that selector. And then it's going to create that endpoint for me. And in this case, I'm doing type load balancer. I didn't put any special annotations on here. If I wanted this to be an internal load balancer, you can look at the Azure AKS docs. You can put annotations on there to say, yeah, this should be internal. This should be internal in this subnet. This should be internal using this private IP, blah, blah, blah. You have all those options at your disposal when you kind of take a look at that document, okay? Pretty simple environment here. But for some reason, when I curl 1, oh, and by the way, we're going to debug this side by side in Kubenet and Azure CNI. You'll see that they're largely the same. In both cases, when I curl 1 instance of the app, it works fine. I get back the message that you just saw here. Hey, we have a Flask container. In the other, it times out, right? So we're going to walk through how we would actually debug this, or a way to debug this, okay? So the first thing I always do if I'm on a call with a customer or helping someone debug is kind of work down from a kind of macro level, the highest level infrastructure, just to make sure the fundamentals are sorted out. And pro tip, AKS ultimately is just a VM scale set. It's a managed VM scale set. So you have the AKS control plane that is managing all of these nodes for you, but ultimately they're just VM scale sets sitting in a network with a route table, an NSG, depending on the configuration, a load balancer. You can see all this stuff if you haven't already, and most of you probably have, in the MC_resource group. MC_resource group is your friend. You should go and look at it. You should understand what components are in there, why they're in there. We'll cover most of them today. You should go and take a look at that. Just don't modify it, because you're going to put yourself in a world of hurt if you start messing with that. And recommend your customers don't modify it either, unless it's something that they're debugging and they're going to back it out, because you're going to get yourself into a bad situation by having that modified. Okay, so high-level assessment. The first couple of things that I take a look at is, one, can you actually connect any other services on this cluster, right? Right. If you can't, then it's probably something like a routing issue, right? So is there a default route, right? So if you go in, if you're familiar with networking in general, you know that in most cases, customers will implement a forced tunneling approach where they'll have a default route that sends all ingress traffic in one direction, or egress traffic maybe has to go through an egress firewall, right? That can cause funky issues, right? Where you have all of your outbound traffic is going out this way, and all of your inbound traffic is coming in another direction. That's called an asymmetric route, right? Because when the traffic tries to go back out, it wants to go back out the way it came in, but it's being redirected out another direction, and bad things can happen. So the other direction will see this packet, say, hey, nobody requested this. I'm not sure where this is coming from. I'm just going to drop it, right? So that's the first thing you take a look at. Is there any kind of funky network routing happening? Can I actually get to the cluster on any other service? In our case, we know that we can. We know we have another service that works, so probably not any routing issues. Do we have overlapping IP space? More relevant in the Kubenet scenario, but still relevant in Azure CNI. I mean, you'd want to make sure that you don't have any overlapping IP space. It's just that with Azure CNI, your IPs are coming from the subnet, so it's more likely that you would see an overlapping IP space issue before you even got to the cluster, right? But with Kubenet, there's definitely a possibility that you could have overlapping IP space, and part of that is because of this this network routing, this route table configuration, which we'll talk about a little bit further along. But in my case, I know there's no default routes because I just created this cluster and I didn't set up any default routes. I know their IP space doesn't overlap because this isn't connected to any other VNets that could possibly overlap. So what are these routes about, right? So if you go into a Kubenet cluster and look in the MC_resource group, you're going to see a routing table. You will not see that in Azure CNI, but in Kubenet you will. And if we zoom in on this a little bit, what you're going to see is for every node that you have in your cluster, you're going to have a route rule. Okay, that route rule is effectively taking the address. I mean, we talked about Kubenet as an overlay network. It has its own address space that sits on top of Azure. Well, what Kubenet does, running in Azure, in AKS, we take that subnet, that overlay network, we call it the pod CIDR, which you can select when you can set that when you create your cluster. There's a pod CIDR. And we split that up so that every single node is getting a chunk of that address space, right? So that as traffic is going between nodes, if I'm trying to go from pod A on node 1 to pod F on node 3, it can find that route because this route table exists and says, hey, all of the pods with IP addresses in this block are on this node, right? And that's how that works. And this is where a couple of things come into play that can impact customers. One, the overlapping IP space. Obviously, if AKS is creating routes for you and your pod CIDR overlaps with some on-prem express route connected address space, there's a possibility that your traffic is going to head out the wrong way and not get to its destination. The other thing that applies here is that you have a certain number of routes that you can have in a route table. Right now, I think it's still set to 400 is the maximum number of routes you can have a route table. So you're going to hit an upper limit eventually and not be able to scale your cluster up beyond a certain point because you might run out of address space here. The last one is if you're in a, I've had this customer conversation the other day. A customer had one route table to rule them all. They had one route table across their entire enterprise, and they wanted to be able to use AKS with Kubenet. Well, AKS was trying to update their route table, which it can do, but it can get very sloppy, very messy, and they really didn't want to do that. So something to keep in mind on that front. All right. So high-level environment assessment, go back to that. Everything seems fine from the highest level. We can access the cluster. There's no funky routing. Let's take a look a little bit further. Okay, there's no NSGs, or well, there is an NSG, but it's managed by AKS, and we'll show that in a second. But the subnet itself doesn't have an NSG. Interesting point here, and this is a point of confusion for some people. If you create an AKS cluster and don't specify a target VNet, it will create an NSG on the subnet because it creates the subnet for you. right? So if I just see AZ AKS create and don't give it a VNet, it's going to create the VNet for me. It's going to create NSG, and it attaches that NSG to the subnet. It does not attach the NSG to the subnet if you're giving it a VNet ID, right? Which is kind of like, can be a little bit confusing, but it's interesting. What it does is if you create, there's always a managed NSG, but if you give it a VNet ID, it will attach the NSG to the VM scale set, not to the subnet, right? And that's important because it allows customers to then bring their own network security group. So this view, we have a Kubenet cluster and an Azure CNI cluster, right? Neither of them at the subnet level have a network security group. And that's because I gave them both the target VNet ID. So they created that network security group at the VM scale set level, not at the subnet level. So now I can come create my own rules. I don't have any rules. So the only NSG rules that are on this cluster right now are those that are managed by AKS itself. Speaking of, if we go to look at the NSG that's managed by AKS, you can see this again in the MC_resource group. So it's named after the node pool, right? We can see these rules here. I can zoom in a little bit and we can see I'm running 2 services on port 5000. Both of them have their own rule. You can kind of guess by the name that this is a managed rule. So AKS went in, and when I exposed this service, it said, cool, I'm going to update the NSG to open up that port at the NSG level. Right now, if we had an NSG at the subnet, it could be conflicting, but we don't. So this all looks good. We're able to get traffic flowing through to this level. Everything looks fine. Okay. All right. So that's kind of the external assessment. We've gone through, we've seen kind of all the high level details about the environment. Routing looks fine. NSGs look fine. Traffic is flowing to other services in the cluster. Okay, so it's probably something internal to the cluster. So let's take a look at that. Before we get into that, I want to do a little bit of a quick sidebar on Azure CNI versus Kubenet, because again, this is probably the most common discussion that we have to have is comparing these two. Okay, so first of all, when we talk about Kubenet versus Azure CNI, pod IP space is probably the most fundamental difference between them, right? So we've talked many times so far in this conversation that the pod IP space for Kubenet is an overlay network. You set it with the pod side, or the default, if you don't set it, is 10.244/16 or something like that. But with Azure CNI, it actually gets that IP space from the subnet itself. There's 2 versions of Azure CNI that are out there. From the core internals, they largely work the same. But in essence, what you have is in the current generally available version of Azure CNI, when you start a node, it will grab 30 IP addresses, and that 30 IP addresses is the default. You can modify that by changing a flag called max pods, because we have by default 30 pods per node that will run. So it grabs 30 IP addresses plus 1, right? So 30 for the pods, 1 for the node. So every single node is going to get 31 IPs assigned to it. Before the cluster is even running, you have those 30 IPs that are bound to the network interface card so that that node can use those. In the next iteration of Azure CNI, it's a little bit different, a little bit more flexible. It doesn't pre-allocate those. It lets you separate node IP space from pod IP space. You can read the docs on that. It doesn't really impact what we're going to run through here. It's just a slightly different way of doing the IP assignment. But in the end, it's still effectively doing the same thing at the low level. Okay. NAT. So in Kubenet, the traffic is always going to NAT to the node IP. If the traffic's leaving the cluster, it's going to NAT to the node IP. Unless it's going, pod to pod traffic won't. But generally, if it's traffic leaving the cluster, it's going to NAT to the node IP. With Azure CNI, it will retain the pod IP address. So if traffic is leaving the node, it's going to retain that pod IP address unless, and this is something that a lot of people don't realize, and is a big point of confusion around CNI, Azure CNI, if the destination is outside of the VNet, right? So if I'm talking across peered VNets, it actually only keeps the traffic with the original IP if it's in the same VNet. As soon as you're leaving the VNet, it actually NATs that to the node IP address, right? So if you're doing, say, network security monitoring in a hub, and your traffic is leaving through that hub, the hub is actually only going to see the node IP. It's not going to see the pod IP. And there's a way you can configure that. It's the IP mask agent config. It's kind of little known, but it's kind of a good thing to be aware of. You might be like, well, wait, I don't understand why I'm not seeing my pod IP from my security monitoring. Well, it's because it's probably leaving the VNet. Okay, service IP space. This is the same. Both of them use the service cider. There's no special configuration here. They're both going to have a overlay network effectively that's created for the services. Route table. So Kubenet, you already saw, we showed a few slides ago that Kubenet uses a managed route table where we add a rule for every node. Azure CNI does not have a route table. So if you look in the MC_resource group, you won't see a route table. So you can bring your own. It's a lot more flexible from that side. Yeah, it's pretty straightforward. Okay. So now digging in a little bit further, comparing these two. If we were to look at a Kubenet cluster side by side with an Azure CNI cluster, they're going to look effectively identical. The pods are evenly distributed across the nodes. The only real difference, and I'll click through the rest of these pretty quickly, is that you can see that the pod CIDR here, the 10.244, doesn't match the node IP address range, right? So this is 10.10 and this is 10.244, versus down here, we can see these are 10.10 addresses, which match the node addresses, which are kind of covered here of 10.10, right? So that's the main difference. Clicking through the rest of these, service CIDRs are identical. External IPs work the same way. You know, that's really it. I mean, the only real difference is the IP addresses of those pods between the two. Okay, so now I mentioned that we're going to walk the stack the hard way, right? We're going to do this a way that I probably wouldn't do if I was doing this myself, but it will help understand. So give me 1 second. All right, so if we look at the stack here, we're going to start from that curl command. The first thing the curl is going to hit is the public IP address, right? So the public IP is part of that MC_resource group. Every time you expose a service from your cluster, you'll see a new public IP gets created in that MC_resource group. Okay, so I can see that looks fine. I can see the public IP address is selected. It's assigned to a load balancing rule, which we'll talk about in a second. All right, the load balancer. When you create an AKS cluster, by default, not doing anything else, you at least get one load balancer. You'll get a load balancer in the MC_resource group called Kubernetes. That load balancer exists for one purpose. It's when the cluster is created, it exists for one purpose. That's for egress traffic, right? So anytime your cluster wants to talk to the internet, it has to go out through some public IP to reach the internet, and that load balancer provides that public IP. As you expose services, they will get added as load balancing rules to that load balancer. If you create a cluster and say, I'm going to use outbound type, which we're not going to cover in too detail here, outbound type allows you to manage the routing of the cluster using your own route tables. You won't get that load balancer. It will just rely on whatever routing rules for egress traffic. If you create an internal IP address, so you create a service of type internal load balancer with the internal flag, you'll get a second load balancer created. So one called Kubernetes is the default one, and you'll have a Kubernetes-internal. Anyway, long story short, that's here. I can see that the load balancer is here. I can see my front end IP address is connected to it. The port 5000 is open. Protocol is TCP. Health probe exists, right? So it's checking to make sure the cluster is available, right? Everything looks fine here. All right. So now let's get into Kubernetes itself, and I'm gonna flip back and forth here between what I'm calling the Kubernetes view and the Linux kernel view. Okay, so the Kubernetes view being the things that you'd see if you're running kubectl, and the kernel view being if you SSH, connect into the node in some way, and look at what is being created within the cluster itself on the node. Oops. So the first thing we see is the service. So we talked about this a bit already. So we have a service of type load balancer. It's on the right port, has the right IP. That all looks fine. Okay, if I take a look at the kernel view for this, the service on the kernel is actually in IP tables. So if I do just an IP tables, the table is nat. So you can run this yourself, sudo IP tables, table nat, and then show me the kube services chain. So IP tables is just chains and chains and chains connected together. So I want to see the kube services chain. I'm just grepping out the Flask app just to make it a little bit cleaner for the screenshot. I can see that here's the rules that exist. So here's my, let's kind of work backwards. The destination. Now this service has both an internal and an external IP address, right? There's the public IP I can connect to it at, and there's the cluster IP address that I can connect to it at, right? So if I come back here, I have 20.81 and 10.0. I can look here, 20.81, 10.0, right? So those are my two addresses. The source in this case is any. So it's saying, look, that's the default route. Any source trying to get to these addresses is fine. The protocol, TCP, right? So protocol is TCP. And then if all of these things match, it says forward this to this chain, right? So in this case, the kube service chain, the kube FW chain is what's the next hop for that packet, okay? By the way, this all is managed through another pod running in your cluster called kubeproxy. So you'll see that if you list all of your kube system pods, you'll see a kubeproxy pod running there that's managing these iptables rules for you. Okay. Okay, so let's keep going a little bit further. So we know we have the service. We know the service has endpoints. We can see that mapping. We've already kind of shown that previously. So I have my service. Here's my endpoints. These were selected using a selector. Okay. Those endpoint addresses, if I take it a step further, 10.244.0.6 comes from my pod addresses. That all makes sense. So from Kubernetes side, I can see, look, I have a service connected to an endpoints, connected to pods. All of that seems to exist and seems to be connected. That looks good. Okay. Taking the same thing, looking at the kernel view, we're basically stepping a little bit further down. So we started with the kube services, and kube services told us that we could next hop to the kube-svc for this. Right, so if I kind of jump back 3, as you can see, kube svc hj y v whatever. Right. Let's take this a little further. Hear that? Continue walking down the chain. Same exact command. I'm just changing this last name here to now show me what's inside that chain. And here I can see there's these kube sep routes here. Okay. And the interesting part here, I should have zoomed this in a little bit. Just good point of information to know if you're running into customers who are having latency issues, maybe they have a very latency sensitive application. You might notice here that there's 3 rules. Okay, I have 3 pods. Okay, so here's my 3 pods, my 3 rules. But you can see this note on the end, statistic mode random probability 0.33. What the heck does that mean? So what that actually means is it's going to select one of these 3 randomly based on this probability, which really translates to thirds, right? So the first rule is going to get selected 0.33 times, a third, 33% of the time. If that doesn't select, it goes to the next one and says, okay, well, I have 2 left. So at this point, it's a 50% probability, either one of these 2, right? So basically, every time you send a packet to AKS or to Kubernetes, it's going to statistically load balance those across the pods in the service. So you might end up in a scenario where your pod your packet comes in, hits one node, and then gets bounced to another node. And generally that bounce, the latency is negligible. It's very small. But if you're dealing with something that's very super sensitive to latency, that becomes important. If you're implementing multi-zone configuration in your node pools, that can become important, right? That now you're picking up these hops. So you need to be aware of that. If you're seeing latency issues, you might want to take a look at that, maybe try running in just one zone and see if it improves your performance issues. Just something to be aware of. Okay, so we have our route here to this kubesep. So it's sending us to the backend pods. And now I'm going to take it a step further. I'm going to take kubesep lb6, whatever. I'm going to sudo iptables that. And here I can finally see, here's the pod IP address, right? So now from a Linux kernel view, I've made it from the service to the endpoint to the pod itself. Same view that we saw on the Linux, on the Kubernetes side. Okay. And we talked about this a little bit already. So I'm not going to drain this, but we do have that route table, right? So for Kubenet, this does come into play. By the way, what I should have mentioned here, unless I say otherwise, this is the same between Kubenet and Azure CNI. I'll specifically call out if there's a difference. You'll see the same thing that I'm showing here in Kubenet or Azure CNI. This is where it's going to deviate, right? So Kubenet has this route table that we've talked about ad nauseum, right? That when the packet's going between the nodes, it knows what node to find based on this address that's been assigned to the node in the route table. Okay. Cool. So taking it the final step, so now we're getting from the endpoint into the pod itself, right? And this is the kernel view. We've already shown the pod IP address is matching the endpoint, but let's look at it in the kernel view. So here, the first thing to do is just do a sudo route. So route is going to show you all of the routes that are in your cluster. This is what it looks like in Kubenet, right? So that 10.244 address space is connected to this interface called CBR0. CBR0 is a standard name for the Kubenet interface. It creates this bridge network interface that all of the pods on a node get applied to, right? So if I go and take a look here, you can see if I do an if config to show CBR0, you can see that it has this address space 10.244.01/24, right? So that's what this this line here is. It's a chunk of that address space. This chunk matches what's in that AKS route table, the managed AKS route table, okay? And then finally, I can go take a deeper look here and see, okay, well, CBR0, if I use this tool called Bridge CTL, Bridge Control, I can say Bridge CTL show, and it shows me all of the interfaces that are connected. Each of these interfaces is a container. Oops. Each of those interfaces is a container, right? So Kubenet is going and creating these container interfaces for you and attaching them to this bridge network, which then gets its address from that overlay network. And that's kind of how all that gets wired up. Okay, I can see this a little bit deeper. So you notice here, I see the interfaces is VF05, whatever. That's not super useful. It doesn't show me what my pod internal IP address is. It just shows me if there's an interface there. I'm sure there's a command out there that will show you that. I couldn't find an easy one. I tend to just go into the pod itself, go into the container itself and check the IP address. And there's a couple different ways you can do that. I know I'm running short on time, so I'm going to try to rip through the rest of this pretty quickly. So what you can do is, we talked earlier about network namespaces, storage namespaces, and things like that. You can actually, from the host node, execute commands into that namespace. Why would you want to do that? Well, first of all, you've created a pod. Maybe I'm just using an upstream, some Flask base image. It doesn't have all my debug and diagnostic tools installed. If I wanted to run Bridge CTL or run, ping, any tool, I might end up having to install all those tools into the container itself, into the running container. And I probably don't want to do that. And I especially probably don't want to do that in a production environment where you don't want to mess with installing things on your production pods. But maybe you're okay installing it on the host node, something just, analysis tools that are a little bit easier to deal with. So what you can do is you can SSH into your node by whatever means necessary. You can, there's documentation from AKS that shows you how to do this. Mine are connected to my home network, like I mentioned. And you can run CRI-CTL to get the details about the running containers. So if I do CRI-CTL PS, it's going to list all of the running containers. So I can see my Flask app. I can see a bunch of the other apps. Here's my kube proxy that we talked about before. I can then get that container ID and inspect it to get the process ID, right? So if I do, and you can grab these commands from this presentation after the fact or find them online, but I can go get the process ID. If I have the process ID, I can actually jump into that namespace. So there's this ns enter command that lets me execute commands in that network namespace. And here I'm just going to I'm going to run the command IP address show effectively, right? So it's going to show me the IP address that's on that pod from inside the container. So this is the container running, and this is the IP that's assigned to it. Okay. The cool thing about this is I can run any command within there. So if there's another network, if I want to run netstat, if I want to run LSOF, which we'll do in a second, all of these things I can do with this command. Okay. One other kind of cool correlation here, I think it's cool, most other people probably don't think it's cool, is that when you do look at the IP addresses that are running on your host, so if you just go to your host and do an IP address show, you're going to see this connection between the IPs that are there. In fact, let me do this really quick. Let's just connect to one of these. Okay, so I do an IP address show here. You can see all of these interfaces. You can see these VFs here, okay? The cool thing about this is they have this VF is at IF3. What does that mean? Well, all of these are numbered. So what it's saying is that virtual Ethernet is actually connected to this actual network interface. So this is the interface that's used by that bridge network to keep things all connected. Just kind of a cool note there. Okay, so where are we now? We've confirmed that we can get the internet to the pod. We can connect to another pod in the cluster. Kubernetes seems to be configured correctly. We've confirmed that the Linux kernel view that everything seems to be there. Nothing's weird, nothing's missing. All the components are there, packets can flow. We know this isn't a firewall because, like I said, we've connected to another pod. So where are we at now? Is the node actually receiving traffic is the next question. Like how do I know that this is actually receiving traffic? And this is where typically I would do the reverse. I would, at this point, I wouldn't have walked this whole stack. I would say, look, I have another service that's running fine. So it's probably something in the cluster itself. And I tend to work from the bottom up, and I start at the pod and then try to connect to the service and kind of work from the inside out. In this case, for the demo, we kind of went the reverse direction. So let's take a look at if the node is receiving traffic. Fortunately, things are configured properly with the Kubernetes load balancer that it is capturing metrics. So if I go in and look at the insights blade for this, I can see everything looks fine, except there's something going on to the backend pool, right? So it's telling me, hey, there's something wrong there. I can dig in a little bit further and see, okay, here's my running service, and that looks good. But the not running service, the 82 service, is having some kind of issue, okay? So now we know, okay, there's something in the cluster, in the node, that's causing this issue. So let's dig in a little bit further. A couple tools we're going to run through. tshark is one that I love. There's other tools out there. There's a kubectl plugin for doing network analysis and getting essentially Wireshark output. It's an extension for kubectl that will, what's the name of it? I'll find and send it out. But will I basically feed that data into Wireshark? I just find that it's a little bit inconsistent. Some clusters, it does feed the data to Wireshark directly, others don't. tshark I've had much better experience with. So tshark is a command line version effectively of Wireshark. So you can watch packet flows flying through your network and see things happening. There's a ton of flags you can set on here. I showed a few of them, right? So you can say, hey, what interface do I want to listen on? You can do capture filters to say, hey, I just want to show what's coming in on port 80 versus 5000 versus whatever. You can then do display filters so that, capture filter is what's it going to look for. Display filters is what's it going to show, right? So I'm going to say, look, just show me the stuff that's an HTTP GET. Maybe I want to filter even further and say, look, I'm going to send some test data, and I'm going to send in the message body the word yo. And just show me the data that contains the word yo in the message body. So really super useful for getting to see your traffic. Because sometimes when you try to look at the traffic that's coming into a node, it can be pretty overwhelming because all the containers are talking to each other and there's all kinds of monitoring that's happening and health checks and all that. It can be a bit hard to find exactly what you want. So using these capture filters and display filters really help you simplify that. And then the last part here is the output format and output fields. And all of this is documented in the man page that I referenced here, but this lets you format the output to something that is more readable, that's important, stuff that you actually care about. So in this case, I'm just showing, filter, or show the output in fields, and I want to show the source IP, source port, destination IP, and destination port. Okay. So let's take a look at this. So I'm just going to do two flows, one against the working service and one against the not working service. Okay. I'm using a tool called Hey, but really you could use your browser, you can use whatever. Hey is a nice tool for sending a bunch of traffic to a cluster. The cool thing I like about Hey is, and you can do this with curl as well, is this disable keep alive. The reason I'm using disable keep alive goes all the way back to that conversation about that probabilistic distribution of traffic and the way the Azure Load Balancer works. So the Azure Load Balancer by default does a hash-based distribution. So it looks at all the backend nodes and it sends traffic using a hash, and the hash is of the source IP, source port, protocol, destination IP, destination port, right? So if you're sending traffic from one source really fast, there's a good chance that traffic's always going to go to the same node because of that hash-based distribution. It's going to say, hey, the source port, source IP, protocol, destination port, destination IP are all the same. So I'm just going to send it to one direction. Disable keep alive turns that off and basically said, yeah, don't do that. Just make sure it's randomized across the cluster. Okay. So in this case, I'm going to send 5 calls. Message body is going to say hello, and I'm going to target my working cluster. And here I can see I'm running tshark on the node, and I can see the output there. Everything looks fine. Do the exact same command and just change the IP address to point to the not working one. And I can see eventually it's going to time out. It's going to fail. And I'm not capturing anything. There's no data coming through. So it's not even getting to the node really. How is that happening? Okay. I can do the same thing with tcpdump. So tshark is really just a friendlier version of what you're getting with tcpdump. So if you're more familiar with tcpdump, go for it. It works pretty much the same. So my hey command, and then I'm going to listen, and in this case, I'm filtering based on the source public IP. Actually, I think I did that in both of them. It's read out because I probably shouldn't be sharing my home public IP address, but I'm just filtering based on traffic from my home public IP. Same deal. One service works, the other service doesn't. Okay. So the question is our app even listening? So this is where a lot of, so many times I've found that this command is useful to see what's going on with an application. LSOF means list open files. Everything in Linux is a file. I don't care if it's a port, whatever it is, everything in Linux is effectively a file. So taking the same process we did before, I can get the process ID from the container, right? So here's the one container that's not working, and I'll show the other one in a second. But here you can see this one is listing on 127.0.0.1, while this one, it is the working container, is listing on this any, effectively, and the pod IP address. Okay, so that's interesting. So they're both listening, but one's listening on the local loopback, the 127.0.0.1, and the other's actually listening on something useful, right? So what's happening here? Let's take a look at the app, okay? So I mentioned earlier I'd show you the app code. It's this simple, dead simple Flask example app. I'm having it run. In this case, I'm binding it to the host IP address of any, right? So 0.0.0.0 in networking always means default. In this case, it means any address that's available binds to it, okay? This looks fine. The Flask app on both sides is working fine. If I look at the Dockerfile, however, we see a little difference. So the Dockerfile, when whoever created this Dockerfile, I didn't even maybe see this. Maybe I just pulled the image and didn't know what the Dockerfile was. Whoever started this command put this flag in here. The working one has the host as the default host, and this one has the host as the loopback. Okay, so one is binding to any address, and one is only binding to the loopback. That's why our LSOF wasn't showing. Okay, so effectively, that's why we were. If I go back here, why we're seeing this issue that we're not listening on the port. Okay, I know we're short on time, but to kind of recap, and I'll make sure we have time for questions at the end here. Key takeaways. First of all, AKS is just a bunch of VMs. There's no magic. Treat it like a bunch of VMs. Look at the MC_resource group. Kubernetes networking is basically just interfaces and routing rules. Like none of the commands that I showed today, apart from maybe the CRI/CTL and doing the NSEnter, that's probably the most complex thing, but it's really not once you get familiar with it. Just think of it as interfaces and routing rules. Take a look. Don't be afraid to take a look and see what's going on. Follow a process of elimination. Start at the high level. Let's look at the macro things. Are there route tables? Are there NSGs? Is there funky network routing that we should be aware of? Is the customer doing forced tunneling? Do they have an egress point? What's their ingress? Are they allowing public IPs? All those kind of really high level, not even thinking about Kubernetes. If this was just a VM, we'd be thinking about the same things, okay? Follow the high level top down or bottom up deep dive, right? So follow up the high level with either, depending what you found, top down, which is kind of what we did, or bottom up, right? So if I see, hey, look, I can't get to any service in the cluster on this public IP address, I would probably start with the top down. In our case, I was able to get to another service. So in the real world, I would have started with the bottom up. I would have started from the pod and worked my way up to see where things were breaking, all right? So maybe you create a debug pod in the cluster, an Ubuntu pod, and you try to curl from there. Curl the pod IP first, curl the service IP next, curl the load balance IP next, right? Working your way up the stack from there. Okay, don't be afraid to dig deep, break things in a safe environment to understand how things work. Create an AKS cluster, tear it apart, understand how things work. Worst case, you delete the cluster and start over, right? All right, so as far as tools that we used, kubectl, obviously, I aliased that to K, so you may have seen me use K, but kubectl is critical for doing this type of debugging. Taking a look at the MC_group, which I've mentioned a number of times today. Don't be afraid to look in there. SSH or debug containers. So there's a doc from AKS that shows you how to SSH into a node, which now it's migrated from doing SSH into using a debug container. I personally ran this cluster locally, connected to my local network, so it made it easier to SSH. I will say personally for me, doing a straight SSH tends to be easier than the debug container. I tend to have terminal issues with extra characters and funky things with the debug container, but you can make it work either way. Load balancer insights. That was super useful to see what's happening with the load balancer itself, that it couldn't access something. So definitely take a look at that, know that that's there. CRI/CTL, so container runtime interface, CTL, I think it stands for. It replaced Docker. So if you were used to using the Docker CLI, Docker PS, Docker pull, CRI/CTL is what you would use today on an AKS node. So get familiar with that. NSEnter, so the ability to enter a namespace, so enter the networking namespace to run commands. tcpdump and tshark that we showed, and LSOF. There's a ton of different ways to show open ports and connected ports, netstat, and things like that. LSOF is just one of them, that I like to use. It's very easy. All right, cool. That was a lot, and somehow we managed to squeeze it in. I want to make sure we open time for questions. Let's see what we have in the chat. Ooh, there's a bunch. Okay, cool. Anyone, rather than scroll through all this, anyone want to jump in? They have an open question they want to throw out there? Awesome. Are ephemeral containers similar to nsenter? I don't know that they're connected. I mean, nsenters is a Linux command, so I don't think. I mean, maybe ephemeral containers are using nsenter in some ways in the back end. It's possible. I'd have to take a look at that. Getting the IPs from pods on a node, you can also use the PID to nsenter. Yep. Yeah. So I'm looking at, you can do that with the same thing. Again, nsenter is an awesome command. There's a lot of different ways you can get into it. I mean, Linux has 10 ways to do anything. See, is there a way to choose between Kubenet and Azure CNI, or any suggestions from your experiences? It's tough. There's a lot of variety. I mean, the big challenge that Kubenet versus Azure CNI typically addresses is the Azure space, and I'm not shy to tell customers to use Kubenet. It solves a lot of problems from a network address space, especially if you're dealing with large enterprise customers. The thing you need to be aware of and you need to keep in mind is a couple of things. One, I alluded to them in this call, or I mentioned them in this call. One, the route table, right? You're going to max out at 400 nodes. You need to make sure you're not overlapping IP space between clusters. Sorry, not between clusters, between your cluster and other corporate IP space. You can use the same pod CIDR between two clusters, and you should be fine, as long as they're not sharing the route table, which is the last problem, right? If the customer I dealt with the other week, they have one route table that they use for every subnet in their environment. Well, then we're going to ugly it up by using Kubenet, because it's going to be inserting routes into that route table, and it needs permissions to do that. And two, if you have two clusters, now they actually have to have different pod CIDRs, because they're both sharing a common route table for their routes. So it can get kind of funky there. But for the most part, I try not to shy away from using Kubenet. It saves customers a lot of time. I know we're out of time here. Feel free to hit me up with questions. Thanks, everyone.